Hey everybody, this is Professor Ross, and in this video we'll be talking about comparing two proportions with a theory-based approach. Let's take a look at a few notes. So in our previous video we talked about comparing two proportions with a simulation-based approach. And with all the different scenarios that we will examine in this course, with the sole exception of a single quantitative variable, all the other scenarios, we will be able to take two different approaches to doing statistical inference. We can do a simulation-based approach, or we can do a theory-based approach. We can always do a simulation-based approach, except for the one quantitative variable. Uh, Whenever we want to try to do a theory-based approach, we always have to be a little careful because we need to meet some conditions in order to validly use a theory-based approach. So that's what we'll be exploring and talking about in this video. And the main way that we carry out a theory-based approach is using the theory-based applet. And so we'll check out an example of that. Our key learning objective is to use the logic of statistical decision-making. So we want to be thinking about our inferential procedures and how we're using logic to make a decision in a scenario. Let's contrast simulation versus theory-based for a moment. In a simulation-based approach, we use shuffling to simulate the division into response categories. So we looked at that in the last video. We said, let's say the number of responses stay consistent. We can shuffle them up to see which categories they end up in, and that would simulate the null hypothesis. We need computing power to do that. And so historically, computers have not always been available, or powerful enough computers have not always been available to really do simulation well. And so historically, often people have used a theory-based approach. Nowadays, the computing power is fairly ubiquitous, and we can always try a simulation-based approach to try these out. One quick warning though, sometimes we have such large numbers that even modern computers can get somewhat bogged down. So if you have samples with many thousands of results in your sample, you may still decide to use a theory-based approach, even though you could do simulation, because the simulator might get bogged down from such a large sample. When can we use a theory-based approach? Well, it uses the central limit theorem, and so we need to meet a validity condition. And the general idea is we need a big enough sample. When you have really large samples, theory-based approach is a great choice. But at the bare minimum, we need at least 10 successes and at least 10 failures. That should sound kind of familiar. But now we need it in each category of response. For each group that we have, we need to have at least 10 successes and 10 failures. If you're thinking about your data in a two-way table, basically what you need in that two-way table is to have at least 10 in each of the four cells representing each of the groups. I'm going to take a look at some formulas here that the central limit theorem uses. These might look a little bit scary, but my main point is not that you have to memorize and use these formulas by hand. Very few people use these formulas by hand. Instead, I want you to see that what we're doing in a theory-based approach is not any different under the hood of what we have done already. So our statistic, if we're focused on the difference in conditional proportions rather than the relative risk or another statistic, this is what the formulas will look like. Our Z statistic, our standardized statistic, has the numerator here of our statistic. And then typically what we see for the standardized statistic is minus the mean of the null distribution. And for these studies, when we're looking at two proportions, the null hypothesis is always that the difference in the conditional proportions is zero. So the mean of the null distribution is always zero. So we usually don't even write it. That's why it wasn't there, minus zero. But this is the same numerator for the standardized statistic as we saw before, our statistic minus the mean of the null. And then the denominator is just kind of a scarier looking formula for the same idea. This is the standard deviation of the null distribution. Now, as I mentioned, you don't need to know how to calculate that standard deviation by hand, but I just want you to see that that's the same thing, and it actually isn't all that different from the other one. We still have p hat times 1 minus p hat. Instead of just divided by a single n, we now have these ratios representing the sample size for each group in our study. All right, so once again, you don't have to calculate that by hand, but we can look at a standardized statistic since it's the same formula, the components are all the same, then we'll interpret it the same way. It tells us how far from the mean of the null distribution our result was. We can use that to find a p-value as well, and so that's what the theory-based approach does, is it takes a standardized statistic and converts it into a p-value. So we'll see that on the theory-based applet. And we can also calculate a confidence interval. And this once again looks kind of scary, but it's really not that bad. It's once again our statistic that's at the heart, the center of the confidence interval, and then plus or minus 2SD. Instead of 2, I have a multiplier because we could use a little higher than 2 for a 99 or a little lower than 2 for a 90. And then SD, the formula-based SD, is this guy here, which once again looks kind of nasty, but it's really just standing for the spread of the null distribution. So let's not do these formulas by hand. Let's use technology instead. In the theory-based inference applet, I have an example for us to try this out. Fukuda et al. In 2002 found some results. They asked families and asked the parents specifically if they smoked or didn't smoke. And so everybody got divided into two groups, the smoking group and the non-smoking group. And then they looked at whether the child of the family was a boy or a girl. So presumably they just had one child, or maybe they were pregnant with a baby, and they looked at the next one was. And here, for whatever reason, Fukuda decided to focus on baby boy as success. We could have easily focused on baby girl as success, but we'll stick with what Fukuda did and looked at baby boy as success. And so the question we can kind of assume we're trying to answer here is, does it matter if you smoke or not, uh, to see what proportion of the children turn out to be boys, right? Is there an association between these variables, smoking or not, and the sex of the child? Or is there no association here? The null hypothesis assumes there's no association. The proportion of boys should be the same for both parents who smoke and parents who don't smoke. Alternatively, coming into this, I would never have guessed one way or the other. So I would simply say it's not the same. There might be more boys, there might be more girls for parents who smoke. I don't know. Let's find out. So you might be able to look at these numbers and get a little sense of this. So it's actually kind of hard to just look at them and figure them out. So let's go to the theory-based inference applet and examine this question. Is there a difference in the proportion of boys born to parents who smoke compared to parents who don't smoke? And I'm going to go ahead and pull up the inference-based applet. Now it's going to be the same one. Sorry, I got it here for us. It's going to be the same theory-based applet that we've used all along. And the reason we can use this applet again is that we can change the scenario here. So instead of one proportion or one mean, we're now thinking about two proportions. And it allows us to put the data in here. Now, this is one thing I wish they would have made a little different in the applet here. I wish that they would have made this look like a two-way table. But take note, it doesn't look like a two-way table. Instead, we've got our ends on the top here, whereas in the two-way table, those are on the bottom. So I'm going to put the n for my smoking group, 565 here, and my n for the non-smoking group, 3602 here. Then we have a choice. We can either put in a count or a p-hat. The table gives us a count of success, 255 for my smoking group. And you'll see when I click away from that, it fills in the p-hat automatically. 45% of my smoking group turned out to be boys. For non-smoking, 1975. I should be able to remember that number. It was the year I was born. All right. So we see a almost 55% of the non-smoking group was boys. This is looking like a pretty big difference. Almost a 10% difference. Let's go ahead and calculate. We can see here 45%, 55%, and yeah, we've got a 9.7% difference. Negative means the higher portion of success is in group 2, right? Small minus big would give me a negative. Okay, I see in my sample about a 10% difference. The question is, out there in the population, should we expect to see a difference? So I can do a test of significance. And here the default is always going to be what we want for the null hypothesis, that the difference of success in the two groups is 0. There's no difference. Now, alternatively, I said I didn't expect one to be higher or lower. So I'm going to just keep clicking until I see the not equals. And I'm going to go ahead and calculate that. Now you can see the blue line for our result way over here and its other tail way over here. We are a long ways away from what the null hypothesis would predict, a 0 difference. We are more than 4 standard deviations below that 0 difference. Is it very likely to see a result that's 4 standard deviations away from what's predicted? No, there's almost no chance we'd see a difference like this in a sample this size if it were really true that out in the population there was no difference in the proportion of boys between these two groups. We have extremely strong evidence against the null hypothesis. We're going to reject the claim that out in the population there's no difference. And in fact, we do see a difference. It appears that out in the population, there's a difference in the percent of boys born to parents that smoke or don't smoke. Which one seems to be higher? Well, just from looking at it, it looks like the non-smoking group is tending to have more boys. In our sample, we saw 10% more boys. Should we expect 10% in the population? How much difference should we see in the population? That's what the confidence interval will calculate for us. So we check the confidence interval box. And here a 95% confidence interval goes from -14 to -5. So how do we interpret that? We feel 95% confident that our parameter falls between these two values. What's our parameter? Our parameter is the difference in the proportion of boys. So the difference in proportion of boys between smoking and non-smoking parents, somewhere between 14% and 5% difference. I'm going to focus on the low end, 5%. We could expect to see at least 5% more boys from parents that don't smoke as compared to parents that do. So that's how we can conduct inference with a theory-based approach. We use the theory-based applet. A couple of quick follow-ups. Do we really believe that this should generalize to all parents? Well, that's an important question. How would we need to answer that? We would need to know how Fukuda et al. Got their sample of 4,000 parents. If they did a truly random sample of parents, let's say in the US, then we should feel like these results do apply to parents in the US. On the other hand, if this was some kind of convenience sample or a voluntary response, we may not be very sure who this should apply to. Another question, do we believe that smoking or not smoking is causing the difference in the number of boys? What would we need for that? We would need to say we have a random assignment to our two groups, smoking and non-smoking. I don't think Fukuda did this. I don't think that would be probably ethical or even possible to do, to force some parents to smoke and other parents don't let them smoke just at random. So so I do not believe we can conclude cause and effect here. There may be other variables associated with this. You could think of lots of other things connected to smoking and sex of the baby that might be at play here. All right, so that's how we can do a theory-based approach to inference with two categorical variables. Oops.